Okay, pipes in series. Let's say you have a system in which you have 3 pipes, okay, of 3 different diameters connected together. Okay, of course, L1 is much larger. It's just for convenience that we have drawn it this way, and you have connected 3 of them together. Let's say Q1, Q2, Q3 are the volumetric flow rates through each pipe. And delta P1, delta P2, delta P3 are the pressure drops across each pipe. Okay, so we have been dealing with a single pipe so far. Now I have connected 3 of them together. What do we know about Q1, Q2, Q3? The same. So Q1 is equal to Q2 is equal to Q3. What do we know about delta P1, delta P2, delta P3? There will be individual contributions that will add up to the total pressure drop, and therefore we can say delta P total is equal to delta P1 plus delta P2 plus delta P3. So what is it like? Q is like current, and delta P is like your voltage, and the friction losses would have been your resistance. Okay. Question is, Q, calculate H total. How would you proceed? So, let's say you have this system, okay, this is the flow rate that you want to get through the system. What is the pump that you have to select? What will you do? Q is given, that means Q is equal to Q1 equal to Q2 equal to Q3. Flow rate through each pipe, that means V1, V2, V3 velocity through each pipe, F1, F2, F3 friction factor in each pipe, H1, H2, H3 head loss in each pipe, and H total will be simply H1 plus H2 plus H3, right? So if you have a complex system like that, you could do it for individual pipes and then add up and then find out the total pressure loss. Okay, of course, I have neglected the expansion and the contraction losses. If you had that, you should have added that also. Simple. Given H total, calculate Q. Okay, you have these pipes in series. You also have got a pump. You want to know how much you can pump. How will you do? Can you tell? So I will take Q as a variable, okay? And then I don't know Q, I need to solve for Q. So I assume Q, calculate V1, V2, V3. That means I can calculate F1, F2, F3 for some assumed value of Q, and therefore I can calculate H1, H2, H3 and calculate an H total as H1 plus H2 plus H3. Check whether H total is as given. If not, go back and correct your Q, and you are right, that's the only way to do it, at least that's the one way to do it. Okay, so it has to be an iterative procedure. Okay, the equations involved are non-linear. you would not be able to really do anything, especially because if you do not know V1, V2, V3, you will not know what Reynolds number you are going to operate. So you might be probably using laminar, the 64 by RE as the correlation, or you have to use anything that will come from Moody's chart or any of the other things. So a priori, you would not even know whether you should worry about your roughness factor or not. Okay, because of that complication, it becomes hard. So one way to do it would be to start with a Q, okay, calculate and then find out if H total matches. If not, go back and check it. Okay, and you know how to do these loops and so on. You know how to solve a set of nonlinear equations, right? How would you solve a set of nonlinear equations numerically? Unless you want to use a MATLAB routine. Of course, you can use the MATLAB routine and do it much simpler. So either way, okay. So it's basically solving a set of nonlinear equations for a given system. That's what it turns out to be. We'll see two more examples tomorrow, and then we'll get into boundary layer theory. Okay. Any question? I don't know. So if it was all laminar, maybe you can write down an expression and try to simplify and get an expression for Q. But a priori, I don't think there is any other way.